Alright guys, so far we have talked about rotational kinematics, which means if you're spinning in a circle, rotating, and we've looked at if you are accelerating, if you're going at a constant rate. We've looked at how that ties into velocity tangential, acceleration tangential. We've even talked about how spinning things have centripetal acceleration. For instance, if you were an ant on a fan blade, you would be rolling around. If the fan blade was accelerating, you would have angular acceleration, you would have tangential acceleration, and because you're going in a circle, you would also have to be holding onto that fan blade with friction, which would be supplying you with centripetal acceleration or force, and you would continue to go in a circle. Okay? Now we're going to get into how you get things to start moving in a circle. Okay? Just like if we wanted to get a mass moving, Newton's second law said we had to put a what on it? Put a force on it. Okay? Now, in order to get things spinning, Newton's second law basically says we have to put a force on it. And when we talk about force in a circle, it's a term that we go with is called torque. Okay? And torque, guys, is basically the force that causes angular acceleration, or tends to cause angular acceleration, and it's really simply put together as an equation: force times lever arm. Okay? Now, if we were to think about a door right here, and this is where the door was hinged, you guys kind of know that if you push really close to the door, it's hard to get the door to accelerate, isn't it? Okay? If you push further out by the edge or where the handle usually is on a door, you can get that door to accelerate a lot easier, right? And so when we're pushing something in a line, it's all linear, it's pretty simple. When we're trying to get something to rotate, it depends on how far away from the axis of rotation that you push as to how hard you're going to have to push to get that thing to roll. Okay? So the amount of torque on something, which is causing the rotation, is going to be basically a function of the force and how big that is, and how far from the axis of rotation the force is acting. Just as a general thing here at the beginning, all torque is going to be positive if it tends to cause a counterclockwise rotation. So for you guys, if I were to push like this, that is causing a clockwise rotation. That's going to be a negative torque. If I push this way and cause that marker to rotate in that direction, in the counterclockwise direction, that's going to be a positive torque. Make sense? Okay. So, how do we look at torque? Well, I'm going to give you, this is the easy example, and then this is where we get a little bit more difficult because we come in at an angle. Okay? Guys, if I have a door right here, and I'm pushing on the end of the door with 15 newtons, perfectly perpendicular to the door, and I have a 1.5 meter door, then finding the torque on that is really super easy. We just take the force, 15 newtons, times the L, which we call the lever arm, which is the distance from that point back to the axis of rotation, and we come up with 22.5 Newton meters. Newtons times meter is a Newton meter. Okay? So that's the units on torque. Now you'll notice, guys, that force is going to cause that door to rotate in which direction? Counterclockwise, thank you. And if it's counterclockwise, then that's going to be a positive torque. Pretty simple. If I were to take that force and flip it over and push that way, we'd have the same magnitude, we just have a negative torque. Pretty straightforward, pretty simple. Okay? Now, where it gets a little tough is when we start, instead of acting perpendicularly, we're pushing on the door at an angle now. Okay? Now I need to make sure I emphasize this. Any force that acts through the axis of rotation is not going to cause any torque. It's not going to tend to get the thing to rotate. For instance, if I came and I pushed right on the end of a door and pushed it in, is that into the hinge? Is that going to make the door rotate? So that does not supply any torque to an object if you push directly in line with the axis of rotation. Okay? So this is called the line of action. So you'll notice here, I've kind of drawn it here. Wherever you point, the force is pointing, that's the line of action. This would be our line of action. If your line of action goes right through the axis of rotation, that force does not contribute any torque. Okay? Now, let's look at this guy. If I have a force coming in at an angle, I think you guys would all agree that I could break that force into a component that is perpendicular to the door and a component that is parallel or acting into the door. Does that make sense? This component right here, because it's acting through the axis of rotation, I know it looks like it's up here, but could I have made this component go like this and like this? So it's acting through the axis of rotation. This component doesn't supply any torque. And I like doing these problems this way. This way, to me, is a little bit harder. But if we break this down, this component, sine 45 times 15, is the part that's acting perpendicular. So that's the part that's actually going to cause the door to rotate. Does that make sense? So my force, instead of being 15, now it's acting at an angle. So it's going to be 10.61, which is the sine of 45 times 15. And my lever arm is still, where that one is acting, my lever arm is still 1.5 meters. Does that kind of make sense? Okay. So we take those two together and we get, in this case, 15.91 newtons for our magnitude. And guys, since this one is acting in that direction, it's going to cause counterclockwise rotation, which would give me a negative torque. What do you think? Okay. I like this. Whenever I have something at an angle, I break it down into its component that doesn't give me torque and its component that does give me torque, and then I just use that component times my lever arm, and I get my torque. Now, there is another way to do it, and each book usually shows you both. Some books only show you one, but I want to show you both. I would solve them this way. They seem easier to me this way, but you can solve them this way as well. In this case, I've drawn the same exact force at the same exact angle, and what you can do, instead of making the force breaking the force into its components, you can actually just continue the line of action. And can you guys see that I've drawn a line that's perpendicular to the line of action? And in this case, instead of manipulating the force, you actually manipulate the distance. And so if you look at here, if this is 45 and that's a 90, does that have to be 45? So what I do there, if this is 1.5 and that's 45, can I say adjacent and hypotenuse and solve for the length of that lever arm? And so if you do that, you can use your force's line of action and then find this shorter distance for your lever arm. And if you do that, you take your 15 newtons times that shorter lever arm, and guys, we come up with the same exact torque, just two different ways to do it. Which ones do you, this one seems to help kids more, they seem to see it better. This one's but it's, the only difference is here you're manipulating the force, so you only have the force in the perpendicular component. Here you're keeping your force, but you're shortening up your lever arm to a point where it would be acting perpendicular. Okay? Alright. Now, that's the basics of torque. Torque causes rotation, and guys, just like we did in a linear sense, we're going to step over, we're going to go into equilibrium. Okay? When the sum of the forces in the x and y were equal to 0, we said we were in equilibrium. Okay? Then the object was not accelerating, right? Now, when we have something and it's rotating, we can say it's also in equilibrium. For instance, this drawbridge right here, which is well drawn, the drawbridge, this is the axis of rotation, the pin that would hold the bridge. There is the knight, there is his trusty steed, and here is the drawbridge cable pulling up. Does that make sense? And guys, the bridge has some weight. And so the bridge is going to also be, if there were no knight and no steed, would the cable still have to hold the bridge up? Okay, so we're going to be at that point. So let's look at this. When we're in equilibrium, sum of the forces in the x equals 0, the sum of the forces in the y equals 0, and the torques have to equal 0. Does this make sense? Now, if we look here, guys, what we're going to do is we're going to find three things. The tension in the cable of the drawbridge, that's T. We're going to find the forces that act on the bridge pin. If this is pulling back this way, is the pin in the bridge going to have to push against the bridge to hold the bridge out there? And then if we got weight standing there, is the pin going to also hold up? Okay. Now, why would you ever want to do this? Well, if you're the engineer of the bridge, you better have a cable that is strong enough to hold the tension, or else your bridge is going to fall in. And you better have a pin in your bridge that isn't going to shear, because then your bridge would not work very well. Okay? I will tell you this, in engineering, you will take a class for one whole semester called statics. And statics is all about things being in equilibrium. And for one semester you will solve problems like this. Okay? With bridge pins and how you put trusses and houses to support the weight. Okay? But let's look at this right here. The mass of the knight, 100 kilograms. The mass of the seed is 600 kilograms. And the mass of the bridge is 3,000 kilograms. Okay? Now, this is something I want you guys to pay attention to. This force, the weight of the bridge, acts through the center of gravity for the bridge. Now, this is a little bit new. We haven't looked at this. But guys, there's weight all along this bridge. But for the sake of calculating torque, how we're always going to calculate torque is we're going to take all of that weight for the whole bridge, and we're going to say it acts through the center of weight. Which in this case, if this is 12 meters long, that center is going to be 6 meters. And so we're going to take the whole weight of the bridge and say that force is acting at a lever arm distance of 6 meters away. Okay, so you'll get a chance to see this in a second. So guys, we're going to solve for this tension. So we sum the torques and set them equal to 0 because we are in equilibrium. So we can say 0 equals the force of the knight times the lever arm of the knight, and it's causing a what? Clockwise rotation. So you'll notice I made it what? Negative. The force of the steed, which is its weight, times its lever arm. We got the bridge times its lever arm. And then we're going to have this cable pulling up that way. Well, it's pulling this way, but its X component's going to be pulling that way, giving us the only positive torque that we have, right? Okay. So if you'll notice, I plugged in the numbers here. The mass of the knight times its weight, times its acceleration due to gravity, that gives you its weight. So we have the weight of the knight times its lever arm, the weight of the steed times its weight of the steed times its lever arm, the weight of the bridge times its lever arm, and remember we just said that it's going to act through the center of gravity, which is going to be half of 12 or 6 meters. And then we are going to have the force of we're going to have the torque caused by the tension, right? Now, if you guys would, we just talked about this component is really going to be acting through the axis of rotation and not giving us any torque. The only component that's going to give us torque is the one that's pulling up, which would be equal to, what do we got here? Cosine of, if that's 40, that's 50. So we got adjacent. So cosine 50 times t. So do you see how I got to cosine 50 times t as my force? And then what is the lever arm distance to get out to that force? 12 meters. Okay. So really, here's what we have. We have the torque of the knight, the torque of the steed, the torque of the bridge, all causing clockwise rotation, so those are all negative. And then we have the torque of the cable pulling up, giving us a positive torque. The only unknown in there is the tension, so we solve. We have to have a cable right here that could withstand 29,348.735 newtons of tension. Okay. Now, if you're an engineer, would you want to over-design that a little bit, probably? Yeah, because you never know. You might have 3 guys with horses coming across your drawbridge. Okay. Now, guys, that is the new part. Does that seem reasonable and logical? Okay. The old part is what we're going to use to find the forces acting on the bridge pin. Now, guys, if you look here, this bridge pin has X forces and Y forces acting on it. So, if it's in equilibrium, we're going to sum the forces in the X, set them equal to 0. In the X, guys, we have that one, and then we have that one. Those are the only two forces acting in the X, right? So I say force of the pin in the X minus sine 50 times T, which we just found T, and we plug it in, we come up with the force in the X direction of that pin has to counteract that force, so it's 22,482.4 newtons. And that's old school equilibrium, sum of the forces in the X. Now if we go in the Y direction to find this Y pin, force Y pin, we're going to sum them, set them equal to 0. We have 0 equals, that's acting in a positive direction. And if you weren't sure, you could just put it in there, and if it came out to be negative, you'd know it was acting downward instead of upward. That guy, the weight of the knight, the weight of the bridge, the weight of the steed, plus that tension going up there, which we know is the cosine of 50 times T. We already solved for T, so we can plug it in there. The only unknown in that whole thing then is the force of the pin, and we can solve for the force of the pin in the Y direction, and so you have to have a pin that can withstand 17,395 newtons. Okay. So, guys, shear strength is if you put the pin in that hole on the bridge, and the bridge is pushing like that, your pin better be able to withstand, in this case, which one's bigger? This one? Okay, that much shear. If your pin snaps, then your bridge is not going to work very well. And your knight and the steed will go for a swim in the mud. So guys, really quick to summarize, and we'll come back to this. We know that torque equals force times lever arm. In equilibrium, we can sum the forces in the X equals 0, Y equals 0, and torque equal to 0. This piece we will come and get in the next piece.